Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today lecture we're going to conclude the main topic regarding dielectric material, regarding material in electrostatic scenario, as what we have tabulated before, the sequence of learning such a issue as stated here, and then we are now discussing the last issue, which is application that we can use in the above components. So the topic of discussion that we're going to go in will be capacitance. So that's what we're going to do now. So I'm going to start with a new page. So we're going to discuss about capacitance. Okay, for capacitance, why is relevant to our discussion? Because in a capacitor, we're going to have a component we know it as a conductor. Okay, that should be exists in a capacitor, as well as in a capacitor there must be a dielectric. And then the field of interest related to capacitance will be electric field. Okay, so I think you can think about application that utilizing this issue. For example, your handphone battery, actually a capacitor storing energy, or even a computer memory is another capacitor storing energy as well. So just in a different way in terms of application, but in a basic concept, there are capacitors that having all these important parameter in it. So that's what we're going to conclude our discussion talking about capacitance. And for those who want to refer to the textbook, you can open to our textbook. If you go to page 249, and then the section here, section 6.5, you're going to see how Sadiku discuss about the topic that we are interested now. Okay, so let's recall an example that I have give before. So let's recall, let's say we call it a power distributor. Okay, in Malaysia, if you in Malaysia, the company that in charge to providing energy to the customer known as Tenaga Nasional Berhad. And then if you look at the transmission line that this company has, usually appear to be, as I shown before, like this. Yeah? So this is a typical transmission line that you have in Malaysia. Different size for different power capacity. So that should be the actual schematic diagram of the transmission line. But in terms of equivalent circuit, as what we have seen or been informed before, equivalent circuit to represent this actual transmission line will be as shown here. So this should be the equivalent circuit that engineer or technician refer to represent the transmission line. And usually this represent what is known as per unit. So per unit scale. That's how they represent the equivalent circuit. And I have mentioned before, the component presenting in the equivalent circuit will be resistor, inductor, and capacitor. Okay, so that's what we're going to see or discuss further regarding the last component, capacitor. As I have informed earlier, why there is a resistance in the equivalent circuit? Because the cable they use for the transmission of power is made of conductor. So once you use a conductor, so that action will contribute to the appearance of the resistance in the equivalent circuit. So now, why there's a capacitor here? So capacitor does not mean you are placing a capacitor in this particular structure, no. Capacitor here, because in EMT, how we define capacitor, okay? In EMT, not in circuit theory. In circuit theory is a device. In our subject, capacitance simply a condition whereby you have one conductor. So let's draw in a general shape because it's ambiguity. The shape of our conductor is not fixed. We're going to call it to be conductor number 1. Then you have another conductor. So let's recall this to be conductor number 2. And then the medium between these two conductors is dielectric. Okay, so when you have this condition, okay, this is the condition that we're having now. So this condition will create what we call it to be capacitance. So for us, capacitance is not a device, it's a condition whereby you have two conductors being separated by a dielectric medium. So let's look into our schematic diagram of our transmission line. You can see here, so the upper cable here representing our conductor number 1, and then the lower cable is representing as our conductor number 2, and you can see the medium between the above cable and the lower cable will be dielectric material. So that is why you will have capacitance in the equivalent circuit. So therefore, what we're going to look at in our syllabus, the capacitance here is the condition of as mentioned here. Okay, so now that should be well understood why capacitance exists, and then that is the general condition that we are stating here. So now the next issue, how we calculate the capacitance. Okay, so how to calculate the capacitance, and then all of you know the symbol of capacitance should be C, similar to the one we seen in other subjects such as circuit theory. And then it's defined by the Q divided with the V, the standard formula that you have seen before. Let's equate this to be equation number 1. So for us to relate this general equation to the general condition is very important, okay, in order to make it viable for us to calculate the capacitance of these conditions. So what we have to do based on this equation, we must place a charge to the system. So what I'm going to do, usually I'm going to say to myself, I'm going to place one conductor with positive charge. So we are creating now, in order to justify us using equation number 1, you have to place charges now. Then I'm going to place another charge on conductor number 2. Okay, and then usually in terms of magnitude, they are the same because the net is equal to 0. We are placing something not there. So therefore, the sum of these two charges is equal to 0. Okay, so it's very important for us to remind ourselves we are putting something not there. So we are creating something not there. So in order to make it acceptable, the sum of these two charges must be equal to 0. Yeah? So why we have to do this? Because the equation said there must be a charge. So therefore, we are putting the charge, but yet to make it a bit safe, when we sum these two charges, the net value is equal to 0. So what happened to this charge? Anyone can say now what happened to the charges that we are placing to the conductor? Okay, good. So what we are saying now, we'll look carefully at this particular location. The medium I'm showing here is a conductor, correct? And then the medium that we are looking here is a dielectric. So what we have now, we have a boundary condition between conductor dielectric. And we have learned about this issue before. So what happened to the condition? So we know that the charge will behave as a surface charge, because that's what we have seen before. When we have a boundary condition conductor dielectric, we know that there's going to be no electric field in the conductor. The electric field will only be in the dielectric region, correct? And then the charge that appear is only known as surface charge located at the boundary. So therefore, that's what we're going to represent now. This is our positive surface charge. So let's denote it to be rho s positive. Okay, and then this negative Q also going to behave as such, going to be a surface charge, so it's going to be negatively charged. So I'm going to represent it to be negative rho s prime. You can see the difference. I'm representing the surface charge positive as rho s, and then the negative charge, negative rho s prime, just to remind me the surface charge may not be the same, even though the Q that we are placing before, they are the same in terms of magnitude. Why this is behaving like this? Good, because the total area of the conductor might not be the same. Okay, that should be the reason why we are assuming, or we are stating, the positive surface charge to be rho s, and then the negative surface charge to be negative rho s dash. So what happened to this, the appearance of our surface charge? Yeah, they are going to create electric field. So that's what we're going to look at, the electric field now. So the electric field going to be the field, vector field, moving from which charge to which charge. Good, from positive to negative. And another condition, that the way the field is behaving, the field must be coming out from the conductor here and then going into the conductor here. So the direction from positive rho s to negative rho s prime, but remember the direction should be normal to the boundary. So whenever you draw the field, must be normal to the boundary, because that should be the issue that we have explained before, the field behavior at the boundary condition between conductor dielectric. So that's what we're going to draw now. Always normal to the boundary. Okay. So let's label the field to be E, the typical field that we symbol that we use. Okay, so now we have placed the charge. The charge now becoming surface charge. The surface charge now producing the field as drawn here, the electric field. So what happened now? So therefore, what we can do now, we can relate the field with the potentials. So the potential that we're going to calculate here must come from the information of the field and the structure. Okay, and what we are saying now, where from our previous lecture, the V must be the potential difference between conductor 1 surface to conductor 2 surface. So I'm going to put negative from conductor to conductor surface, E dot dl. So I'm going to put here conductor, for in this case, conductor 2 surface to conductor 1 surface. So I usually choose the limit of my integration to be opposite to the direction of the E. Why I'm doing this? Just to ensure that the final result I'm going to have for this particular calculation will end with positive numerical value. Right? That's only the reason. If you use your limit the other way, when you have negative solution, you can just change to positive just to make it acceptable. Okay, so there you are. So that should be the task that we are going to use when we want to calculate capacitance later on. But now, remember that when you calculate resistor before, we use the resistance. Okay, recall resistance using what method? Yes, using field theory. So in the equation of calculating resistance, we have to use electric field for the results. So similarly now, I'm going to convert my capacitance equation using the above method, field theory. So now what I'm saying, I see Q is the charge, V I can see this electric field, so it's something relating to our electric field. So now my interest now to convert the Q in terms of electric field. So therefore it's justifying what I'm saying here. I'm going to calculate capacitance using field theory method. So all the components that appear in the final equation will only consist of electric field parameter. Okay, so let's do it now. So what I can do now for Q, okay, so I'm going to convert Q into electric field component now. Okay, for Q, so Q here, you have to consider only one of the charge only on one of the conductor. Okay, that's why it's not the sum now. The Q again should be referred to the charge on one of the conductor. So usually I'm always choosing the charge that having positive value. So therefore I'm going to see the Q is the charge. I'm referring to the conductor 1. Why? Because it's having the positive charge. So I'm going to take sample. So this is my sample now, dq. Okay, so now to find the Q from our week number 2 lecture, we need to sum all the sample of the charge, correct? Then we know based on our model of surface charge, the dq should be represented with rho s ds. Okay, yet refer to our boundary condition conductor dielectric. Okay, so I'm putting note here, refer to the boundary condition conductor dielectric. So what's special about this situation? Anyone can help me? What's special about it? Yes, because we know that the D must be equal to rho s an, correct? That should be the equation of the D. Remember that the equation that we derived together? Okay, so now if I want to find the rho s, what should I do then? So if I said rho s equal to D dot an, is it correct? Is the equation is acceptable? Yes, let's substitute now. Okay, now I'm substituting now, this term now, I'm putting here now. So that's what I'm going to get now. Rho s an, that's come from the substitution. Then I'm going to dot with an. So an dot an will give us what? 1. So therefore, that's how we extract rho s from the equation of D. So now if I place this equation here, I can see that this equation is becoming integration. Okay, D dot with an, that should be our rho s, agreed? And then we are multiplying with our ds, that should be the output of the substitutions. Now, if I'm looking at this particular term, what is saying to me now? So this term contain magnitude, correct? And directions. So that should be known as what? Yes, this is known as our vector ds. So in other words, I can say to myself, the Q, okay, finally I can say the Q here actually is equal to the integration of d dot with ds. So now what actually I'm doing here, I'm converting the Q component equation to be represented in terms of field parameter, because the D is known as epsilon E. So now if I want, okay, now I'm using from 1 again. So I'm going referring to, okay, from 1 now. So referring to equation number 1. So the capacitor now is equal to what? The Q integration of epsilon E dot ds, agree? That should be our Q now, because D equal to epsilon E. The dielectric contain parameter epsilon. And then divide everything with minus E dot D. Okay, therefore, this should be the equation that we're going to use to calculate capacitance based on the field theory concept. Okay, hope you can see now. It's quite similar in terms of approach when you are calculating resistance, where you have to determine the suitability of electric field. Then you use the actual structure given by the problem to find the resistance. So now it's similar here. You have to find the electric field, and using the actual structure and material in the problem in order to determine the capacitance. So therefore, so that's what we're going to do now. We're going to do example to show how this equation can be utilized. But still remember, but please be remember, the method that we're going to adopt is quite similar to the one that we have used in finding resistance before. Okay, so let's do one example now. Okay, so example, I think this type of equation, this type of problem is a popular problem to be given in test and final exam. So please understand the method well, because I think it's no point in memorizing solutions. Better you understand, and then from there, inshallah, you're going to have full marks in your effort. So example, let's say that's what we're going to do now. Example. Okay, so I'm going to put example 1 to be systematic now. So let's say now, I have a parallel plate capacitor. Okay, a parallel plate capacitor. So that should be my top conductor. And then the medium between the conductor, usually I'm going to place what is known as a dielectric. So, and then I have another conductor at bottom here. So therefore, this should be our parallel plate capacitor. So this is a parallel plate capacitor. Okay, so important parameter now is the area. So I'm going to put the area to be A. And then the distance here, so let's make it to be D. Yeah, so that should be the physical dimensions. And then this conductor 1, the bottom surface should be our conductor number 2, and the medium between the conductor should be dielectric. And how we represent dielectric? Good, with parameter known as epsilon. Yeah, permittivity, as what we have explained before. That's what important, dielectric to be represented by this parameter. So now, if you have this structure, so this structure will have capacitance. Okay, therefore, logically, the question asks what? Find capacitance. Yeah, that should be the question. Okay, how to find the capacitance? Actually, there's a formula for it, but we're not going to use the formula. We're going to derive it. Hopefully, you can see the step now. From the step that we're going to make the problem becoming more complex later on by adding a lot of dielectric between the conductor. But inshallah, if you understand the concept, whatever you do later on is just straightforward. It's a similar method. Just redo again. So what we are doing now, so just repeat again what we are saying now. Okay, to find the capacitance. Okay, so what I have to do, step number 1, placing the charge. So I'm going to place, in this case, I'm going to place this step, the bottom conductor with charge Q, and then the upper conductor with charge negative Q. Okay, and then because the area of this conductor the same, I'm going to say myself the surface charge density going to be positive rho s at the bottom, and then the negative charge density negative rho s on the top conductor. As you can see, since both conductors having same area, therefore the charge density must have the same magnitude. Okay, so that's done. So what happened to this charge? They're going to produce electric field. So you're going to produce from where to where? Good, from positive to negative. So that should be the way I'm going to draw my field, positive to negative. I'm ignoring the fringing effects, just assuming is from bottom to top conductor. So this is my field E or D, doesn't matter. So now, how to find the field? So that is what important now. Okay, so the E, okay, I'm just putting here now, the field D should be the, okay, step number 1, placing charge. So the charge is going to produce the field. So now I'm going to calculate the field. D can be determined by using which method? Okay, yes, Gauss law. Okay, or you can use Coulomb's law with infinite surface charge assumptions. Yeah, but I'm going to use Gauss law. And then from Gauss law, if you look at the notes, I think you can see that the D should be equal to rho s. Okay, so I'm going to put axis now to make this mathematics better. So I'm going to put this to be my z-axis, this particular side to be my x-axis, and this particular to be my y-axis. So what should be the direction of the E? The D? Good, z direction. Or some of you want to say, no, I don't want to use the boundary condition. I don't want to use the Gauss law. So I'm going to use boundary condition. Doesn't matter. Put another statement here. I can use boundary conditions. Okay, boundary conditions. Conductor, dielectric. You can use that as well. Doesn't matter. But inshallah, both methods will end with the same field value. Okay, so that's all. Now you can see this one EMT is very many methods that you can use. But remember, the method that you use is something that you feel comfortable. I can use Gauss law, having this as my solution. I can use boundary condition, conductor, dielectric that we discussed before. Same, this is my condition. So that's done. Yeah? So therefore, that should be my D. Okay, then I'm going to put now E. Okay, the E, as you can see, E referred to the inside the dielectric, equal to what now? D equal to epsilon. E equal to D divided by epsilon should be rho s over epsilon z directions. Okay, so that should be the field. So the most important thing for us to always to make sure the result is okay is to determine the valid electric field. Okay, unable to find the correct electric field, whatever approach that we are doing after this is going to be inaccurate. So even though the method is okay, but the result will be inaccurate. So for me, still I'm going to give marks, because for me, not the result is very important. The process getting the result is important. That's what always life is all about. Yeah, the process getting your results. When you become engineer, that is very important. Okay, now, so let's proceed now. Okay, then we have the E. So finally, the capacitance. So C now, as we know, is equal to integration of what? Epsilon E dot ds. Remember the equation that we derived together, divided by minus E dot d. So remember, this equation must be related to this diagram. Okay, so I'm going to relate them together now. So integration, epsilon, okay? So rho s over epsilon here, z direction dot with ds. So ds here should be dx dy in z directions. Okay, the one that we learned in week number 1. Okay? Taking area sample. So this is our ds. Okay, so dx dy direction, z direction. So we place it here. Okay, so now that's done. So divide everything with now minus E again, rho s over epsilon z dot dl. So dl should be the dl there based on our Cartesian table equation. That should be n with dzz. Okay, so now I'm going to choose the limit. So I'm always choosing the limit of my potential different mathematics opposite to the direction of my E. Since the E is moving from down to top, so my limit should be from D to 0. Okay, because this position is D, this position is 0 based on the z-axis, and then this should be area A. So I put it here. So my final solutions, inshallah, going to be what now? Okay, I can cancel this term and this term. Okay, should be epsilon A over D. So that should be the solution. See, very simple, very straightforward. Just follow the step carefully. I think you can obtain the correct results. And then most of you can already memorize the formula. So this is a typical capacitance formula for parallel plate capacitor in other subjects. So we just prove it using what method here? Field theory method. Okay, so let's make it a bit challenging now. So let's do example number 2. I'm still referring to the same structure just to show you, even though it's a bit complicated but not difficult, so we can use the above results in our process here. So let's change our capacitor to be as such. Okay, so I'm going to draw the same area top. Okay, and then there's a dielectric here. Okay, so the axis, I'm going to make it appear to be as above, z, x, y. Dimension here, I'm going to call it to be d. So the only difference in this particular problem, the dielectric material. Yeah, dielectric now, we're going to have 2 dielectric placed. So this should be, it's still conductor. So this conductor, but this dielectric different now. So let's state this one to be epsilon 1, this one to be epsilon 2. Okay, so therefore the above area, to make it systematic, the above area here, okay, is A1. So the area that not shaded is A2. So, okay, they're having different value of areas. So that's the problem now. So find the capacitance. That should be the question. Okay, so let's do it now. I think in terms of method, let's do it together as what we have done. So we're going to place charge. Okay, so I'm going to place charge now. Bottom charge, above charge. So I'm going to put out, should be Q. This should be minus Q. So the question now, do the charge distribution of charge, surface charge density going to be the same above the dielectric medium epsilon 1 compared to the dielectric medium epsilon 2. So can we say that the charge here should be rho s, here should be rho s as well? Can we do that? Okay, do you think that the charge is going to be the same when we place the Q? The charge density going to be the same when we place it on the conductor? We're not sure, correct? So let's prove to ourselves now. Okay. So, but we know that this charge going to produce what? Electric field. Agree? So now they're going to produce electric field. So I'm going to draw this one to be black in color. This electric field to be red in color. So to indicate to myself, I'm not sure whether they are the same electric field in terms of as what we see up here. Electric field the same throughout the medium. But here, is it going to be the same or is it going to be different? So that's what we're going to answer. Okay, so to answer that issue, we have to go to this particular location in our problem. So let's zoom it now. Okay, I'm going to zoom. Okay, so now what we have a boundary, correct? And then the medium on the left is epsilon 1. Medium on the right is epsilon 2. So let's draw the field now. So I'm going to draw the field here, red in color. So, and then I'm going to draw the right-hand side field black in color. Okay, so this is what we are having now. So if you look into this particular diagram, have you seen this diagram before? Yes, we have seen this diagram before when we talk about what? So refer to, okay, boundary condition number 2. Number 2, remember? When you talk about dielectric boundary condition number 2, yeah, as you are saying, E T1 must be equal to E T2. Because the field now is acting as what? Normal component or tangential component to the boundary. So this is our boundary, remember? So the field now is acting what to the boundary? Normal or tangential? Yes, tangential. So this is E T1, this is E T2. So they must be the same. So in order for us to say they are the same, we must say that E1 must be the same as E2. So, and D1 not the same as D2. You see? Only the E is the same, the D not the same because D equal to epsilon E. So, if the D not the same, and we know that in general, the D, so this refers to boundary condition conductor dielectric, rho S AN. So therefore, since the D not the same, therefore the rho S also will be not the same. So now we have to make it clear. So this particular region, going to be filled with rho S1, and this particular region going to be filled with rho S number 2. See the logic now? Oh, sorry about that. Okay, so now the rho S cannot be as what we have stated up here because the reason of the field, the E field, they are the same in region number 1 compared to dielectric region number 2. But the D field, the electric field density, they are not the same. And the charge on the conductor dielectric boundary condition will relate to the D. So since the D not the same, therefore the charge also not the same. Okay, that's done. Okay, so that's already done. Alhamdulillah. Okay, so I'm going to put now. So what we are saying now. So capacitance. So let's calculate the capacitance. Let's make it systematic now. Okay, so now the capacitance C is equal to Q over V. Okay, and the Q for me should be equal the charge on one of the conductor. So I'm going to refer to the bottom conductor, should be equal to the integration of dq1 plus dq2. Okay, so what is dq1? My sample here, I'm going to call it to be my dq1, and my sample here, I'm going to call it to be dq2. And then if I do the mathematics correctly, this is going to be n with rho s1 a1 plus rho s2 A2, correct? Because just charge multiplied with the area as what we have done up here. Charge multiplied with the area. Yeah? Rho S A1, rho S A2. Okay, that's done. So now, let's see, how about the V? Okay, the V now, okay, for V is equal to minus E dot dl. It's not D dot dl, it's E. And I know the E in both medium, they are the same. So regardless if I'm using E1 or I'm going to use E2, they are still giving me the same output because the E is the parameter that we use to calculate the potential difference. Okay, so it doesn't matter. So now I'm going to use. So which one that you want to use now, E1 or E2? So let's take it to be E1. Okay, so now E1 is my E. Okay, how to calculate the E1 now? So the E1 should be equal to minus the integration. Okay, D we know. So D1 rho S1 AN. E1 should be rho S1 divide with epsilon 1 z direction dot with dl. Okay. Now, limit from where to where? Good. D to 0 should be equal to rho S 1 over epsilon 1 D. Okay, that should be our potential. So it doesn't matter you use E2 because we're going to cancel this later on. So now what we can see now, we can see, oh, our capacitance. Okay, so now I'm going to put capacitance C equal to, just substitute now, rho S1 A1 plus rho S2 A2 divided with rho S1 epsilon 1 D. So it's not complete yet because we have so many variables that are ambiguous. Because remember, the charge is what we place. So when you place inside the problem, you cannot let it to be appear at the end of your solution. So it's not acceptable. Something that you put in cannot be a parameter in your final representation of results. So you have to do something. Okay, so I'm going to now to cancel the rho S. So I'm going to say, okay, let's say now I want to place rho S2 in terms of rho S1. Okay, can we do that? Because when you do that, then all the rho S can be cancelled out in this particular equation. So now how to do that? Okay, we refer to this equation. Okay, call this equation. Okay, what's special about these equations? E1 equal to E2. What should be E1 equal to? Okay, rho S1 over epsilon 1, correct? How about E2? Rho S2 over epsilon 2. So, can I say now, rho S2 equal to epsilon 2 divided with epsilon 1 rho S1? Can I do that? Okay, yes, we can do that. Alhamdulillah. So now let's put that in our equation here. So I'm going to place now this to be epsilon 2 over epsilon 1 rho S1. Okay, so we done that. Okay, now so let's simplify the mathematics now. I can cancel the rho S now. Alhamdulillah, rho S cancel, rho S cancel. Now, how about the epsilon 1? Okay, so I can do that now. Okay, so what I'm going to do now, I'm going to move the epsilon to the top position now. So this one going to go up, should be epsilon 1 A1 plus, if I put it up here, the epsilon will cancel out. I'm going to end with epsilon 2 A2 divided with D farad. So that should be our final solutions. Okay, so there you are. So I'm using field theory again in my calculations. Okay, so that is a thing that you can do. So now let's ask a problem now. Just make it, it's quite similar, but this is the one that you should do yourself. Okay, just to test your understanding. So I'm going to go to example number 3. But you have to do it yourself here. I'm not going to show you here. So you try it first. But if you got problem, please mention to me. This is important because usually the question that I ask and then you should do, if nobody asks me, so that is my popular question in my coming quiz. Yeah? So that should be the normal thing I'm going to use. Because nobody asking me, so I presume you understand. So therefore, it's good for me to ask your understanding by asking you again in the quiz. So this is the problem example 3. So you have the same structure. Parallel plate capacitor. Okay. Okay, so this conductor having area A, but now what's the difference now? The dielectric now is being assumed to be in this particular condition. So this particular thickness, let's make it to be D1. So this second thickness to be D2. Why? Because the dielectric here, let's say epsilon 1, let's say here epsilon 2. So question as before, find the capacitance of this structure. Okay. So that should be the problem. You try and do it, but please use a field theory approach. Please do not memorize formula because you can say solve this problem again using a formula that you know before, because the capacitor is in series, and when capacitor in series, there are formula that you can use to calculate the capacitance. So please do not do that. You can use that to verify your result, but please do not use that method in this calculation. So what we want to know here, the concept of field theory, because structure-wise is similar. But what happens when the structure becoming a bit complicated? So therefore, formula not more advised, not more good to be used, because when complicated structure, we always have to go back to fundamental method. Okay, so to test that, let's do example number 4. Okay, so let's say find the capacitance per unit length of a coaxial cable. I think you have seen this problem given to you in the quiz number 4. So let's do here. Okay, so what we have now, coaxial cable. So same to the structure that we seen in quiz number 4. Okay, you're going to have a conductor. So that should be the first conductor. We call it the core of your cable. And then you're going to be surrounded by second layer here. This usually known as dielectric. Okay. So, and then you're going to be covered with the second conductor. Okay. So that should be a coaxial cable. Okay. So conductor 1, conductor 2 very thin, and then the medium between conductor 1 and conductor 2 is a dielectric. So let's give dimension. So the inner cable, as similar to your quiz number 4, A, and the outer conductor, let's make it to be B. Okay, and then the medium here, dielectric, I'm going to state now. So the dielectric now, okay, to have permittivity epsilon. Okay, so therefore, find the capacitance per unit length of our coaxial cable. So let's recall our basic method. Good. So first thing, I'm going to place charge. So I'm going to place first the charge here to be Q, and the charge here to be negative Q. And then the charge will change themselves to become surface charge. So I'm going to place now positive surface charge on the inner conductor and negative surface charge on the outer conductor. So I'm going to replace this with rho s, and here I'm going to give it with negative rho s prime, because the density, they're not the same value, because the area of the given conductor not the same. Okay, now, how to find the capacitance? So we already know the charge distribution. So again, I'm going to say using Gauss law. Okay, so the electric field density in the dielectric, okay, I'm going to find the field in the dielectric now, is, I'm going to use a formula, remember d dot ds equal to what? Q enclosed. Then what should be our Gaussian structure? Yes, similar to the example we did before, should be a cylinder. So now I'm going to have, should be equal to dr 2 pi r h. Remember, h is the length of our Gaussian profile structure, should be equal to rho s 2 pi a h. That should be the Q enclosed, the charge that residing on the inner conductor, A, radius A. So this is the charge we are calculating on the inner conductor. So that should be Q. Now the D, in terms of vector now, should be equal to rho s A over R in R directions. Okay, so therefore the electric field intensity now, okay, electric field intensity E should be equal to D over, not epsilon naught, good, epsilon. Because we are given now dielectric epsilon, so we must put it there. So the solution of E should be rho s A over epsilon R in R direction. Okay, so that's how we obtain the field from what method? Gauss law method. So now let's find the capacitance. So finally the capacitance, okay, C should be equal to epsilon E rho s A over epsilon R in R direction dot with ds. What should be the ds? R d phi d z, correct? And the R should be placed with what? Because we are calculating the charge where, so this should be placed with A. Do we agree? Okay, that should be our Q, rho s ds, okay, epsilon E dot, so now this is the formula. Okay, I'm going to divide everything now with the V minus rho s again, rho s A over epsilon R, R directions, now dot dr R. So the limit from where? From B to A. Okay, that's substitutions of our C. So let's simplify the mathematics. Okay, I'm going to cancel rho s with rho s, A with A, epsilon with epsilon. Okay. So this is going to be equal to 2 pi, okay, 2 pi A L. L is the length of the cable, so not similar to the H. L is the length of the cable, and then that should be our rho s, okay, 2 pi A L. Do I miss something? Yes, the epsilon. So put the epsilon there. Yeah, the epsilon still there. It's not cancelled. Then I divide everything with, okay, 1 over R dr. Let's go ln P over A. So the question asks us what here? Capacitance per unit. So now I have to place the L to the left now. So now I'm going to change the solution to become capacitance per unit length. should be C divided with L. Okay, just take this L, put to the left, should be equal to 2 pi, can I cancel the A? So 2 pi A epsilon divided with, what is it? Ln B over A farad per meter. Oops. Okay, that should be the solutions. Okay. So just check again whether the A is still there or not. Because, okay, the dimensions, okay. 2 pi A L, okay, that should be then ln B over A, it's okay, that should be epsilon, good. Okay, so inshallah, I think the solution should be acceptable, so that should be okay. Okay, so there you are. Okay, so alhamdulillah, I show you how to find the capacitance now using a very simple method. Okay. Okay, thank you very much, inshallah. If any problem, anything that not accurate, maybe we can, you can ask me. Maybe I can check again my work. But anyway, thank you very much. Inshallah, we're going to see again. So I think in my next lecture, going to be talking about something totally new, because the method that we are using here is only applicable to for a dimension of problem which is uniform or something that easy. So in terms of when you're dealing with the complicated shape of problem, this method going to be a challenge. So therefore, in order to solve those type of condition, we're going to have to use another method, which is going to be mentioned in my coming lecture. Okay, thank you very much. Okay, take care. Assalamu alaikum warahmatullahi wabarakatuh.